So first, I got a lot of screens open that I want to talk about. So this was the picture that you guys saw in the video, and it just kind of gives you an idea of how area works in polar. What makes it so different are the boundaries. Instead of thinking like left to right or bottom to top, we actually think of it as like rotating like hands of a clock. Again, we're rotating in counterclockwise direction. So when we write down our boundaries, we are saying where do we start, that we call it a radial line, and then where do we end? So you have that like kind of rotation effect going on. The definition of area, obviously it's super wordy, but the only thing you need is you need to make sure you have this formula written down. Anytime you are finding area, it is going to be 1/2 the integral from the starting radial line to the ending radial line of the function of theta squared. So we can write it as f of theta squared, or we can just say r squared. And I did one in the notes so you kind of got to see it. So what I want to do now is I want to show you a delta math one, because I think it's pretty cool how delta math will like really show you more. And then I want to go to the PowerPoint and show you what that looks like. So again, I have so many screens open. So let's go to delta math first. So here is a question from delta math. So with area, there are two types of area questions. In a normal year, I do all of area in one block because I can get it done. It's just kind of a busy day. This year, I'm not. With everything going on and the fact that we have a little bit of time, what I want to do is I want to break area up into one curve area, which is today, and then two curve area tomorrow. So we'll kind of start with the more basic ones today and then have that step up tomorrow. So tomorrow's still area. It's just looking at multiple polar curves instead of a singular one. So the most common type of curve that you're going to work with are rose curves, which are my favorite ones to do. So you're going to be given an equation of a rose curve, and they are going to ask you either to find half of a petal, one petal, or the whole thing. And truly, none of them are more difficult. Once you find the area of one petal, you just then have to count how many petals there are and multiply to get the whole thing. If you wanted a half petal, you could do that. I actually use half petal a lot because of the symmetry. You could do that really quickly. So this one has a rose curve. It has 7 petals, and we know that from the 7 that's in front of theta. The 8, again, represents how long the petal is. So you can see this one goes out more of your radial, like your radius circles. And it wants you to find the area. With delta math, it is going to ask you to round to the nearest thousandth, which is perfect. That's exactly what I would want you to do for me anyway. So your first step with this is you need to figure out your boundaries. So you need to find that, we call it a tangent line to the pole. So if I draw a ray that starts right at the pole out, where does it just touch the edge of that petal? So to do that, this one's already totally done in delta math. I just wanted to kind of like talk you through it. To do that, you're going to set the equation equal to 0. So you're going to set 8 cosine 7 theta to equal to 0. Obviously, the 8 doesn't matter. It's basically just saying when does cosine of 7 theta equal 0. You do need to know when cosine equals 0 and when sine equals 0. So cosine is going to equal 0 at pi over 2, at negative pi over 2, at 3 pi over 2. I mean, really, it happens over and over again. As long as you know the first couple, you're good. Sine will equal 0 at 0, at pi, at 2 pi. So knowing those basic units circle for sine and cosine help. So if we set 7 pi or 7 theta equal to either pi over 2 or negative pi over 2 and divide by 7, we get these as my boundaries. So what that's telling me, if I go back up to the picture, is my region, and I can use this little slider. So this starts at negative pi over 14, and it starts to trace it all the way through, and you can see that area filling in, and it will trace it all the way until it gets to pi over 14. So we start at negative pi over 14, we end at pi over 14. Now another option is you could just go from 0, which is this polar axis, to pi over 14, and then double your answer. That would give you half of the petal, then double it, you get the full petal. So your setup, here's your setup. So my formula is 1/2 the integral from start to finish. So this one did negative pi over 14 to positive pi over 14 of your entire function squared. So you put all of that in your calculator. You do not have to be in polar mode to do these, but you do have to be in radian mode, and make sure you square the whole thing. And then you get your answer. You do not have to have an exact answer. They think that a decimal is perfectly fine, and I agree with them. And your decimal answer is 7.181. If it would have asked for the entire area, I'm going to have you do like one of each for homework, like one that's a half petal, one that's a full petal, one that's the whole thing. All you have to do to find the total area is take this answer and multiply by how many petals. So if you go back up to the picture and you see it has 1, 2, 3, 4, 5, 6, 7 petals, if you multiply this answer by 7, you would get the full area. If you divide it by 2, you would get the area of half a petal. So you can really take half petal, and full graph and do it all at once. So that is just the Delta Math one. Obviously, if you start working on them later today and you need more help, you can always look at examples or watch some of their videos, but I think they lay it out. They do a good job of laying it out. I didn't like what Delta Math did for derivatives, which is why I did not assign it, but I do really like what they do for area. All right, so let's do some problems here. So here's our first one. This is a rose curve. I don't know why they say one loop. I wish they would have said one petal. This one wants to find the area of one petal of the curve r equals sine 2 theta. It's a very small one. If you graph this on your calculator, you see these tiny little petals because they're only 1 unit long. See what you can do with this one. This one says new calculator. Ignore that. Use your calculator. I have no problem with you using your calculator. So see what you can do with this one. I think you know what the answer is. Obviously, you will have to mess around a little bit with your calculator to get the decimal that you hopefully got on your calculator to be equivalent to one of the exact answers on the screen. All right, everybody's getting C. I actually didn't get C. Did you remember to multiply by the half?
Since it's from 0 to pi over 2, shouldn't it just be 0 to pi over 2 and not multiply the 1/2?
The 1/2 is always part of the formula. That is actually from the formula. It is 1/2 the integral from start to finish. So the picture, I actually drew a picture down at the bottom. So this is what it looks like. If you were to graph it on your calculator, to do that, you would have to switch it to polar mode. You get this 4-petaled flower. And your first petal I say first petal because it's in the first quadrant, is entirely enclosed between 0 and pi over 2. So we don't need to really use any symmetry at all. We're going to go from 0 to pi over 2 of the entire sine function of 2 theta, square that whole thing. The 1/2 is always there. It is not part of the symmetry. It is truly part of the formula. So you should get 1/2 the integral from 0 to pi over 2 of the sine of 2 theta all being squared, and you actually should get B. So if you got C and just forgot the 1/2, that is an easy fix. And if you made that mistake on the first one, no big deal. But yeah, there is always a half there unless you then use some sort of symmetry and like doubled it and canceled out. But in this case, it truly is just this region right here. And the way we find those boundaries by hand, if you don't have the picture handy, is you set sine of 2 theta equal to 0, sine equals 0 at pi, so you divide by 2. And then you get those boundaries. If it wanted the entire rose curve, you would then take that answer and multiply it by 4. So that's your first one. All right, next one. Okay, here's your next one. This one, I'm trying to think if I have a picture of it somewhere that I could draw. I will, I'll draw a picture on my calculator and draw it on the screen. This one actually, you don't need to do any extra work to find the boundaries because they tell you the boundaries. This is the best situation in a polar equation, is they tell you what the boundaries are. So this one is super straightforward, and you can and should use a calculator. I'll let you start, and then I'll graph it on my calculator so you don't have to, so you get an idea of what it looks like. So this one, if you graph it, it looks a little distorted on the calculator, but it's actually a circle that just isn't centered at the pole. So it looks like this. That's a horrible circle, but it has this circular look for it. So it is going all the way around from 0 to 2 pi, which is why they just give you those boundaries. Yeah, this looks good. I see Danny, I see Claire, you both said D. You guys are exactly right. The setup of this one is really quick. It is 1/2 the integral from 0 to 2 pi, since they gave you boundaries, of just that entire function being squared. And then you get a decimal answer that you'll have to switch. The decimal answer, just to make sure everybody was on the right track, is 51.836. On a test or a quiz, I have no problem with you writing 51.836. This one, they wanted you to convert that to a exact answer, and it does end up being D, 33 pi over 2. Nice. I like the ones where they give you a lot of information and it takes a lot of it off of your plate. This is another one that actually gives you some pretty good information. So this one wants to find the region that's bounded. It's this little like sliver. They call it R. I cut and paste this picture from an AP test. They tell you that the one curve, like the curved part, is 4 cosine theta, and that the linear part is the line theta equals 1, and it wants to find you to find that area. One of the boundaries is given. I'll give you that as a hint. Your lower boundary, it's going to start at 1. I think your upper boundary, you can just stop at pi over 2, because you'll notice that this, like, it almost looks like a petal, stops at the end of the first quadrant. So it never goes any further than pi over 2, since it's all situated in quadrant 1. So see what you can do for this one. And this one, obviously, you need a calculator because your decimal answers. All right, Danny and Claire are on things today. It is B, that is correct. So your setup for this one, it's another really quick one. Since they give you a picture and they also give you your lower boundary, and with the picture, you could figure out your upper boundary without doing any work. You are going from 1, because that's this lower radial line, and then you're stopping at pi over 2. That's going to be that tangent line at the pole. You can kind of see I didn't draw it right. It just goes straight up here. You still have the 1/2 out front. You still have the equation squared, and you do get B, 0.465. And this one's kind of interesting. I'm going to kind of give you a little chance, a little at a time to start this. This is not a multiple choice. This was one that I kind of copied and pasted, and I also pasted my work. So I'd like you to start the process by writing down your equation. So what this wants is it wants the area between the inner and the outer loops of the limison. A limison is the one that has like this little loop. It actually looks a lot like, let me draw a picture here. It looks a lot like, that's a horrible picture. It looks a lot like that, though, that it has like this outer almost circular piece and then this inner mini like loop. So what I want you to do first is I want you to set the R equal to 0 and see if you can figure out what those angles are. And then I'm going to kind of like talk you through piece by piece of how to do this one. All right, so let me show you what you should have got so far. I think I have this revealing a little at a time. Yeah. So here should have been your first step. So your first step is to set it equal to 0. You can subtract 1, you can divide by -2, and you're trying to figure out what makes the sine of theta equal to 1/2. It does take a little unit circle knowledge here, or obviously you could grab a calculator and just double check what you think makes it 1/2. It happens at pi over 6, and it happens at 5 pi over 6. So here's what this looks like. So don't mind the handwritten piece here, but I like this picture. I thought it kind of explained it well. So you have this limison where it looks like it's kind of like opening downward, and you have this little like teardrop inner loop. What the problem wants is it wants to find everything except for the loop. So it's like you're finding like the whole area, and then you're subtracting out the loop area. So let me explain to you what the boundaries are going to do here. I have a little bit labeled in the picture, but I'm going to write on a little bit more just so you can kind of understand what's happening here. This one to me needed the most explanation on my part. So if you were to graph this on your calculator, and the really nice thing about having a calculator close by is you can use it as a tool to kind of like mess around with these pictures. If you type in this equation and you go to your window and you change your theta values, you can kind of see like what's going to make the loop, what's going to make the whole thing. And what you end up seeing is if you just graph from pi over 6 to 5 pi over 6, so this like in between angle piece, you would get just the loop. So going from pi over 6 to 5 pi over 6 creates that inner loop. If I want to find the area of everything else, I actually have to keep going around the circle all the way until I get back to the pi over 6. So that is going to be starting at 5 pi over 6 and then going all the way around. To get all the way back to pi over 6, you would have to go to 13 pi over 6. It's like you're adding that extra revolution to it. That's going to give you the entire figure. So that's going to get like everything in there. We want the stuff that is there without the loop. So I hopefully all of that explanation, I'm going to give you a few minutes because this can take a little while to set up. You will have to set up 2 equations. There's your hint. We need to figure out what is the area going to be if we don't include that inner loop. I'm going to give you a couple minutes and let you go with that before I show you how it gets set up. And you are going to get lots of decimals. And yes, Danny, I am acknowledging that your pi over 6 was perfect for your boundary. So sorry, I didn't mean to ignore that. As you're working, kind of continuing with my hints, you will have to set up 2 definite integrals. One is going to represent your inner loop area. That's the part that you don't want to include. And then one is going to represent the entirety of the area. When you are done, you're going to have to utilize both those answers that are going to both be decimals. If you get the answer and you feel comfortable, I would love for you to put the decimal answer of the final, that's the filled in area without the loop, put it in the chat. My last clue is that the final answer is somewhere between 8 and 9. So if you got something between 8 and 9, tell me what you got. All right, we got 3 answers. They're all the same, and they are all right. So let me show you. I actually have, rather than being subjected to my horrible handwriting, I have it ready to appear, hopefully, maybe. There it is. So here's what you should have set up. And when I do these, I like to kind of label things like area 1 or area 2. And this is going to be really helpful, especially tomorrow when we start looking at multiple curves and we have different things happening. So area 1 is what I called the inner loop area. It's the integral from pi over 6 to 5 pi over 6 of that function squared, and then the 1/2 out front. And it's a really small answer. It's 0.5435. And then area 2 is what I'm calling basically the entire figure. So 1/2, that's going from 5 pi over 6 to 13 pi over 6 of the function squared, and you get 8.881. To get the area that I shaded in, to get the area that was not including the inner loop, I want to subtract. Just like in regular geometry class, when you'd want to find an area of something that has a part missing, you subtract, and you do get 8.338. How are we doing? Everything okay with this? All right, so I want to come back to my face and stop recording.